we're trying this with table form. That's next to the fifth times the sine of 2x. Normally this would take 5 integration by parts iterations, but we're going to do it in table form. Put all the derivatives of x to the fifth that we can get out of here. Then all the antiderivatives of the trig function right there. But tell me, what's the antiderivative of sine of 2x? Going to have a 1/2 out front, right? So it's going to be a negative 1/2 cosine of 2x. Every time you take an antiderivative, you get another factor of a half. So let me go ahead and finish off my derivatives. We'll have a 20x cubed. We'll have a 60x squared. 120x. And 120. You can't stop until you hit the row of zeros. So your table's going to have 1, 2, 3, 4, 5, 6, 7 columns in it. Now remember, each time we take an antiderivative, we get another factor of half. The integral of cosine is a positive sign. So I keep that minus, and I'm going to minus 1/4 sine of 2x. The integral of sine is a negative cosine, so the next time I'll have a positive 1/8 cosine of 2x. The integral of cosine is a positive sign, so I'm going to get a 1/16 sine of 2x. Now I'm going to get a negative 1/32 cosine of 2x. And then finally, a negative 1/64 sine of 2x. So you have to remember to integrate by getting that extra factor of 1/2 out there. Now we go down the diagonals. Our first term in the antiderivative will be a plus that product. So the first term is going to be x to the fifth times a negative 1/2 cosine of 2x. And I'm going to put it in the order of the coefficient, then the polynomial term, then the trig. And we change the sign on the next one. The next diagonal has a minus 1/4. We have to change the sign on that one. So I'm going to have a positive 1/4 times 5x to the 4th. Put the 5 and the 1/4 together. And then we're going to have sine of 2x. The next one, we keep the sign. The sign is going to be a positive. Let's take the 20 times the 1/8, then the x cubed, and then the cosine of 2x. So I'm going to have it's positive 20/8. If you want to put a 10/4, you can, or whatever that reduces to. X cubed cosine of 2x. So So that was the plus. The next one is a change the sign diagonal. So let me indicate that I'm going to change the sign on that one. That becomes a negative 60 over 16 x squared. And this time the trig function is the sine of 2x. The next diagonal, we keep the sign. We're going to have a negative 120 over 32 times x. And now we have a cosine of 2x. We've got one more to go. I've got the 120 times the sine of 2x. This is the other term. Alternate, minus, plus, minus, plus, and now minus. So I got to change the sign on that one. That gives me a positive 120 over 64. Times the sine of 2x. And we're done. So let's happily apply a plus C. Don't try using the table on just anything. It's got to have polynomial term. And if this won't work if I had a fractional exponent, it's got to have a column that has a derivative of 0. Okay? Okay, so let's look next at, let's see, last time we did, I don't remember, we did logarithm, we did we do any of the inverse trig functions? We did? Okay. Let's come up with something here.
You wanted to try the e to the x times like sign.
Want to do that one next? All right. I kind of wanted to do a conventional one first before I did that one.
Like a inverse.
Okay, we could try one of those. Hand out for you guys on this. Oh well, make one up then. Let's try integrating x squared times the inverse tangent of x. Now that x squared is going to make you say, well, I want to do this in table form. The only problem is you don't know what the antiderivative of the inverse tangent is. That's not, we know the derivative of the inverse tangent, but we don't know the antiderivative of the inverse tangent. So we can't do that in table form. There's no way I can finish the second column. So we're just going to do this with our general UV minus integral of V du formula. And since I don't know how to integrate the inverse tangent, that's automatically my U. The same is going to be true if I had an inverse sine or a logarithm. I don't know how to integrate any of those. Those, if they appear in part of the integrand, will automatically be the U term. That leaves me with the x squared dx as the dv. So we're going to take U to be the inverse tangent of x. And dv is x squared dx. Then you have to take the derivative of the u term and the antiderivative of the dv term. Now, the derivative of the inverse tangent is the one that's the 1 over 1 plus x squared. When you integrate the x squared, you're going to get x cubed over 3. And so my scheme here, let me work this out. Over here is where I put the uv minus the integral of b du. Again, I'm going to try to write that every time so that it'll help you learn. U times v is going to be the product of the inverse tangent of x with the x cubed over 3. I always like to put my polynomial term first. Now my v term comes next, x cubed over 3 times the du. Du is 1 over 1 plus x squared dx. And we're hoping that new integral is something we know how to do. It's a product, and I can't integrate each factor in a product. So I'm going to simplify that second integral so that it looks like an x cubed over 1 plus x squared, and then I'm going to pull the 1/3 out front. So let's swing it up higher. Yes. Oh, the arrow, right to there. We'll take the 1/3 out front. And then I'm going to slide the x cubed on top. Then I'm open for suggestions on how to do the x cubed over 1 plus x squared integral. Oh, I don't. That's not there. Thank you. What do we say when the numerator is greater degree than the denominator? Divide. If the numerator has higher degree than the denominator, then that's an improper fraction. We can simplify it by dividing. So let's divide. Let's do the dividing over here. I'm dividing 1 plus x squared, which I'm going to write in descending order, x squared plus 1, into x cubed. So I could say I need a factor of x, multiply both of these terms by x, and get x cubed plus x. And then subtract that line from the line above it. Did I see where the x cubed plus x came from? So when I subtract that line from the line above it, I lose the x cubes, but I get a minus x. And since this is degree smaller than that one, this is considered my remainder. So I can write that fraction over there as the whole part plus the remainder over the divisor. So let's keep our x cubed over 3 inverse tangent of x minus 1/3 the integral, the whole part was the quotient term, plus the remainder is the negative x over the divisor. But I'm gonna take this minus sign and I'm gonna put it right here. But doesn't that look goofy to you? So let me move that minus sign down in front. Right here. Since this integral has two terms that are subtracted, I can integrate term by term. So this one's easy. I integrate that x and get x squared over 2. What about this integral? That's a UDU integral. The degree on the bottom is 1 less than the degree on the top. So that's a hint that it's an ordinary UDU integral. Take u to be the 1 plus x squared, and du is going to be the dx, the x on top. That's just for this one. So I'm going to put a new integral sign here. Keep in mind that that 1/3 is on both of them. So I'm going to take u to be the 1 plus x squared. Du then is 2x dx. I'm keeping the x dx, replacing it with 1/2 du. So let me clean it up. I've got the x cubed over 3 times the inverse tangent of x. Now I've got the negative 1/3 times the integral of x. That's going to be an x squared over 2. Now I'm going to take this negative 1/3, put it here, that makes a positive 1/3. Then I've got the 1/2 from the du term. And then I've got the integral of 1 over u du. So we integrate that 1 over u du and get a natural log of u. And here's our final answer. We get the x cubed over 3 times the inverse tangent of x minus 1/6 x squared plus 1/6 times the natural log of u, where u is 1 plus x squared. So 1/6 times the natural log of 1 plus x squared. Then finally tack on the plus c. So again, anytime there's an inverse trig function or a logarithm as part of your integrand in a product, those are automatically the u's, because we don't know their integrals. And everything else is the dv. You gonna remember that? There's the remainder over the divisor. Remainder over the divisor. Right? Okay, now some integration by parts calculations give you a resulting integral a few steps down the line, the same as the integral you start with. Those kind of integration by parts problems I call circular. You end up in an infinite loop if you keep trying to do integration by parts. So once we recognize that our original integral comes back to us, then we treat it as an algebra problem. That typically happens when your integrand is the product of exponential functions and trig functions. So let's do one of those. I'm going to integrate. Now, how about e to the 4x times the sine of x dx? First thing is to give away that it's integration by parts is that it's a product. We can integrate either of the two terms, so it doesn't matter to me which one you choose to be the dv. Doesn't matter at all. You'll get the same sequence of steps. I'm just going to take u to be the e to the 4x, and then the dv term to be the sine of x dx. Then we take the derivative of the u term. The derivative of e to the 4x is itself times the derivative of the power. So I'm going to get a 4 right here. Then the antiderivative of the sine of x is minus the cosine of x. So up here we put u times v minus the integral of v du. So in our example, u times v is going to be a minus e to the 4x cosine of x. Then we subtract the integral of v times du. So look at what you get when you get a v times du. You can have a 4x, a 4 e to the 4x times a negative cosine of x. I wanted you to see this minus sign that came from the negative cosine of x. I'm going to take it here and make that a plus sign. Okay? So these two minus signs are going to make this a plus, and I'm going to rub it out with my hand. But I've got a product again, exponential function and trig. So that tells me integration by parts again. Keep the same strategy you had at the beginning. I chose u to be the exponential function, so I'm going to choose u to be the exponential function again. So we're going to integrate by parts again. Keep u to be the e term, so I'm going to take the 4 with it. 4 e to the 4x is u, and dv is cosine of x dx. Now we take the derivative of 4e to the 4x. The derivative of the exponent is going to throw in another factor of 4. So we get 16e to the 4x. Times the dx. Integrate here, integral cosine is a positive sign. So I'm going to move down here. We're going to copy this first term. It's part of the antiderivative. Minus e to the 4x cosine of x. Plus, and now in here, I'm going to do the integration by parts step. Do our u, v minus the integral of v du, using the stuff above me. So u times v here is going to be 4e to the 4x times the sine of x. Minus v times du. V times du is going to have a 16e to the 4x times the sine of x dx. So minus the integral of v, sine of x, I'll put the 16e to the 4x, sine of x here, dx. You with me? These brackets here aren't holding anything. There's not a coefficient here, there's not a negative sign here, so these brackets are useless. I'm going to take them off. But normally there might be a minus sign here, so be careful. All right, now I'm going to take this 16 and I'm going to factor it out because e to the 4x sine of x is what we had originally. So in the next line, I'm going to write all that. So there's the integral that we started with. In fact, it's still sitting over here. I'm going to put it right here. It won't do me any good to do more integration by parts because I'll just keep repeating the same 2 steps that I just did there. So this is why I say stop. Stop integrating by parts and now make an algebra equation out of it. I've got one of these here. I've got minus 16 of them there. I want to put them together. So I'm going to add 16 of those integrals to both sides to give me 17 of them over here. So move this over. Add all of this to both sides. Right, so if I add it over here, it's gone. If I add it over here, I'm going to have 17 of them. And I still have the first 2 terms there, minus e to the 4x cosine of x, plus 4e to the 4x sine of x. So what do you think the last step is? Divide by 17, and we've got the integral that we want. Once you cancel it here, you have the integral you want. Tack on the old plus c, put a circle around it. There's the antiderivative. So the things you need to be careful of is not losing minus signs. You've got to make sure that you end up with something over here that you can add back over here, and not losing coefficients. So I tried to keep my coefficients inside until the very end. It was only at the end that I pulled the 17 out. And I kept them as part of the du and the dv terms. Very easy to make algebra mistakes. Okay, so there's one of those on your whiteboard. Yes, sir. Well, then you'd have to distribute it. Well, if you pull it out, put it out here, and then in the next step, distribute it back through. Right? Because if you keep stacking up parentheses, that's when you lose them. You try to simplify each step as much as you can before you do another integration by parts. I think you'll be, and it will help to have some neat handwriting. Sorry?
You don't pull anything out until you have the original.
Until I have the original one back, and then I pull out that last coefficient. And if I have a constant up here and a constant in there, man, those bad boys are all over the place. You're just going to have all kinds of little things to pay attention to. So just try to do your steps nice and neat. Keep track of your constants. Okay. Okay. You have enough of integration by parts? I think so. I think you're going to try it to learn it. Okay. What's next? What's in the next section is the biggie. The For some reason, always the third section of every chapter is the one that's the long one. In section 7.3, we've got to learn how to integrate trig functions a little bit better. We can integrate sine to the first power, sine to the second power, but we should be able to learn how to integrate sine cubed, sine to the fourth. Same deal with cosine. We have a formula for the integral of tangent to the first and tangent to the second. What about cubed and fourth? Secant, first, second, cubed and fourth. So we're going to look at those integrals. I guess we're going to start by integrating secant cubed. Because surprisingly enough, the integral of secant cubed and the integral of cosecant cubed by itself is an integration by parts problem. And it's an integration by parts problem that becomes circular. So let's try integrating secant cubed right now as our bridge between this section and the next one. So here's another circular integration by parts problem. But you don't know that by looking at it. I know it because I've been in this profession for a long time. When I was a student, this was on my calculus test. I thought, holy smoke, how do you do this problem? It doesn't even really look like a product, right? If I tried this to be U and this to be DV, I don't know that I get anywhere. Let me show you. I'm going to do it. Don't write it down. If I try integrating it by parts, the way it looks, I'll just pick U to be the secant cubed and dV to be dx. What's the derivative of the secant cubed of x?
3 secant squared.
Bring the power down, raise it to 1 power less, but then you multiply by the derivative of the inside. What's the derivative of the secant of x? Secant tangent. So we get 3 secant cubed of x times the tangent of x dx. Here, what's the integral? What do I get as my v? Well, I get an x. So think ahead in your integration by parts problems. You'll have u, v, minus the integral of v times du. You get a much worse integral back because you're going to have an x now with higher powers of secants and a tangent showing up. So that doesn't stand a chance in heck of being a second integral that we know how to do. This makes a bigger mess. So we scrap that idea. Another way to write this as a product is to kick the most out of here that I know how to integrate. Well, we derived a formula for secant, the integral of secant to the first power that had a natural log in it. Does anybody know how to integrate a secant squared?
Tangent.
That's a tangent. So I'm going to break this up with a secant times a secant tangent times a secant squared. And now I see that the largest part I know how to integrate is the secant squared. So I'm going to pick that to be the dV, and I'm going to pick that to be the u. This one's going to work, so go ahead and write it down. We take u to be the secant of x, and dV to be the secant squared of x dx. the derivative of the secant of x is the secant of x times the tangent of x. And the integral of secant squared is a tangent. So now let's write down our integration by parts. Over on this side, we're going to put uv minus the integral of v du, with the hope that the v du integral is easier. So u times v gives me a secant of x times a tangent of x, right here. Minus the integral of v times du. So I'm going to have a secant times a tangent squared. Now we're going to stare at that second integral and see if it has any help. If that wasn't a tangent squared, I can integrate secant tangent. If it was a secant squared times a tangent, then that's a UDU integral, right? Because drift tangent is secant squared. So it's neither a UDU integral or a known integral. So I could try integration by parts again. But I'm going to stop and do some trig. I know there's a relationship between tangent squared and secant squared. What is that trig identity? That was hard to remember, but we all remember this one. Sine squared plus cosine squared is 1, right? Close. That's right. If I divide everything by cosine squared, there's my tangent squared, plus 1 is secant squared. That's what I'm going to use right now. But I'm just going to substitute out the tangent squared for secant squared minus 1. So I'm going to replace this with secant squared minus 1. It's when I distribute that secant through there that I get my original secant cubed integral back. And then I'll have minus the secant of x in there. I'm going to take this integral of 2 terms and write it as 2 integrals. But remember, there's a minus sign out here, so I've got to distribute the minus sign back through here. And so we'll be able to rewrite that as the secant of x times the tangent of x minus the integral of the secant cubed of x plus the integral of the secant of x. This is the integral we started with. So we're going to add it over here to the one that's sitting right here. Do you remember the integral of the secant of x? One that I added to your list and said it's time to learn that one. Got a natural log in it. Natural log of the secant x plus the tangent of x. So we're going to integrate that one. We're going to move this one to the other side. There's one of them over here. Let me write it right here. So I'm going to add it here to get 2 of these here. And then I still have this here. So our final answer, when I divide by that 2, is that the integral of the secant cubed of x dx will be that entire right-hand side divided by 2. Right-hand side has a secant of x times the tangent of x plus the natural log of the secant of x plus the tangent of x. Then I said I'm dividing by that 2 that's in front. And now I'm done. And I tack on a plus c. I showed you that one because integrating odd powers on secant, secant to the 5th, secant to the 7th, secant to the 9th, those are all going to be circular integration by parts. And there's such a pain in the rumpus to do after a while that there's a power reduction formula for the integral. I can never remember that. If you look this integral up in a table, or if you have one of these integrating thingies on your computer to integrate it for you, you're going to get something that doesn't look quite the same because it's using this formula. And you remember, you can rewrite trig expressions in a whole bunch of equivalent ways. So, okay, so let's remind ourselves now, as we go into section 7.3, which trig functions we know how to integrate. There are going to be 3 parts to section 7.3, or maybe just 2. We're going to integrate combinations of trig functions, combinations of sines and cosines, combinations of tangents and secants. And then once we learn how to do that, then we're going to do some integrals that have radical signs in them. And we get rid of the radical signs by making clever trig substitutions. And after we make a trig substitution, we get a trig integral. So the first part is learning how to do trig integrals. And the second part will be integrals by trig substitutions. We're going to look at 2 types of trig integrals. We're going to look at integrals of combinations of sines and cosines, where the sines and cosines are going to have powers. So let's say we've got the sine of to the nth power and the cosine to the nth power. We're going to have a couple strategies based upon whether m and n are even or odd or a mixture. Same deal with tangents and secants. With an mth power and an nth power, and different combinations. Then if you did cosecants and cotangents, it would satisfy the same strategy as we have here. So I won't even cover the cosecants and cotangents. But what you're going to need to know are your basic trig integrals and your basic trig identities. So we already know these. The integral of the sine of x minus the cosine of x. The integral of the sine squared of x was x over 2 minus the sine of 2x over 4. You know the integral of the cosine of x is the positive sine of x. And we know the integral of the cosine squared of x is x over 2 plus the sine of 2x over 4. Not going to worry about the secants and tangents. We do know that when we take the derivative of a sine, we get a cosine. When we take the derivative of a cosine, we get a sine. And we also have a Pythagorean identity that relates sines and cosines. And like I said, the derivative of a sine, the cosine, and the derivative of cosine has a sine in it. Those are important because we're going to try to do a lot of these integrals as u du integrals. And if we can't do a u du integral, then we make a swap with even powers of sines and cosines. We had another trig identity that helped us get this and this. Do you remember where these came from? We used a trig identity for the sine squared of x to get me an in-between step to get this. So here's another trig identity. The sine squared of x, we said was the same as 1, what?
Plus 2 sin x.
Not the integral, just the identity. It was 1 minus cosine of 2x over 2. The cosine squared of x was 1 plus the cosine of 2x over 2. And tell me how you would do this integral. I've written anything on the board that makes that an easy integral to do. You can, but there's no reason to.
You could just say use,
Always look for a UDU substitution.
you say use sine.
If u is the sine of x, du is the cosine. And this is just a u cubed du integral. Right? This is easy. Look for the UDU part first. If you've got a sine in your integral and a cosine in your integral, if there's one of them's to the first power, then you've got a UDU integral. That's going to be true if one of them's to an odd power. Let me look at this one. Here's the same example, kind of. Let's keep the sine cubed here. And now make that a cosine squared. Each of those individual terms has its derivative as the other part of the integral. If I take u to be sine, du is cosine, but then that leaves me an extra cosine flopping around. But if I take u to be cosine, du is the sine, and what's left over?
Sine.
A sine squared. That's okay to have a sine squared left over, because I can get rid of a sine squared. A sine squared is 1 minus cosine squared. If you have an integral that contains sines and cosines, and one of them has an odd power on it, factor one of those out and put it with the dx term. pull one of the sine of x out, pull it out to the first degree. And then we're going to try to write the rest of the integral in terms of cosine, using our Pythagorean identity. So I'm going to keep sine squared here, cosine squared here, and then the sine of x dx. If this is going to be my du term, everything else has to be in terms of cosine. So now I have the opportunity to substitute out the even power of sine. So I see this as my du term. So write everything else in terms of cosine. That means I'm going to replace this with 1 minus the cosine of x. Minus the cosine squared of x. So now if I take u to be the cosine, I've got a polynomial integral. Take u right here, be the cosine of x, du is minus the sine of x dx. So minus du is the sine of x dx. And I can take that trig integral and write a polynomial integral. I'm going to have a 1 minus u squared times u squared times the minus du. There's the minus du. Is that an easy integral to do? Plot out, integrate term by term. Yes, sir.
Why did we introduce a negative in the du?
Because the derivative cosine is a minus sign,
Oh, okay.
so I got a negative out there. So you multiply this out in here. And then integrate. So I can distribute that minus sign, replace the u's with my cosines. I'm sorry, yeah, each u is a cosine, so I have minus cosine cubed of x over 3. Minus a minus gives me plus. Cosine to the 4th x over 4 plus c. Yes, sir.
So why don't we take u as cosine x?
I only took u to be the cosine because the other term had an odd power. You've got to be able to factor one of them out, leaving even powers left.
No, I told you that. What I'm saying is, when we have 1 minus cosine squared, all times cosine squared, when we make the sign,
Right?
we can make it towards 1 minus u squared as well.
Well, I didn't want to pick a cosine squared.
Like, what I mean is that like we could take u to be. How is that like real time to have u to be a single time? You know, go across.
Well, you can go across. That's what we're going to do all the time with our trig integrals. Okay, so I'll write this down next time as a strategy. When one of the powers is odd and the other, who cares? If any one of them's odd, we're going to factor one of them out and then use the Pythagorean identity. So we've got a bunch of steps in this section. This is just our first step to get you to recognize some of these things. What's the matter?
There-
Fifth?
no.
Yep, you're right. Partial credit? You gonna bless me on that one?
Partial credit?
You got lots of partial credit.
True.
Actually, yeah, I think you should just be counted right. It seems like a good.
Just can't, wrongs are right, rights are
100%
wrong.
credit.
All right, thank you guys. All right, any questions from any of you guys at home? Yeah. Always, thank you, thank you. a lot of homework up here too. So. Thank you.
I just, because we were, you know, I don't want to walk this snow. I don't want to walk on the road.
Look at
Yeah,
that
it's bad,
handwriting,
it's bad. Yeah, I'll work on it. Don't see me really shop.
Vegas, one of yours right on top. Come on back.
What's up?
I got one of yours right on top of your head.
Oh, okay. Look how nice the handwriting is. You probably tell how nice it is.
Yeah,
I apologize for this too. That works backwards. in my
that's
paper.
okay. What do I got? Do I have it in yours?
All right. Thank you.
You're right, I don't have one. Thank y'all.